to be bonded to two different groups, which they are. Like if you look at this carbon atom, that's one group, and this is your other group. So they are two different groups. If you look at your other carbon atom, it's got an H, sorry. So it's that carbon atom is bonded to a CH3 and it's also bonded to an H. So this carbon atom is bonded to two different groups. This carbon atom, I mean, you have to think of the whole side. Like it's got one group over here and it's got one group over here, and they're both two different groups. So that means if that condition is met, and it is non-cyclic. So if that condition is met, then it will form cis trans, and this butene molecule would exist in two ways. There's going to be a cis version of that, and there's going to be a trans version of that. So is that clear? The first thing, how do you identify whether a molecule makes cis trans or not? Is this clear?
Yeah. Yes, sir.
So let's let me do another one. Let's say I have this molecule. Will this form cis trans? This one is a carbon. Does it meet the conditions?
No, sir.
No.
Okay. Remember both carbon atoms. I mean, it's got a double bond, but remember each of the carbon atoms must meet the conditions. This one does because there are two different groups attached. This other one does not, because on both sides there is an H attached. So it's definitely not. So there's not going to be any geometric isomers, no cis trans for this one. There's only going to be just one version for that. There's only going to be one three-dimensional shape for this molecule. So that's the very first basic idea of when a molecule would form cis and trans. Now the next thing, yes.
In the first molecule which you've drawn,
Hmm.
if the second carbon had the hydrogen attached downwards, it will still form a cis trans, right?
This one? Actually, this
Yeah,
one.
this one.
I told you that the direction of the bond does not matter. I mean, because this is not the actual shape of the molecule. Do you get my point?
Yeah.
Because carbon is tetrahedral. It doesn't, I mean, the hydrogens don't look like this. So it doesn't really matter at the moment whether the hydrogen points upwards or is it pointing downwards. Is that clear?
Okay.
So always remember, all of the molecules, all of these structural formulas, they're not the actual shape. So I told you that if the H over here is pointing downwards, it's still the same thing. It's because structural formulas, they tell you the connections, like who's connected to what. So it doesn't matter if the H is pointing to the right or to the as long as it's bonded to the same carbon atom. So now we're going to discuss what is cis trans. Now cis trans, when you have a double bond, what happens is when you have a double bond, carbon is sp2 hybridized, which means what that means is carbon is bonded to just three atoms. And so carbon is just bonded to three atoms, like a fan. It's bonded to three atoms. There's an atom one over here that's pulling the electrons. So one of the electron gets pulled to the right. One of the electrons gets pulled in this direction. And one electron, just like a fan. Think of this as a fan from a side view of a fan. And here's an atom that's pulling the electron in this direction. And it's got a fourth electron, which initially is not doing anything. So the fourth electron is not doing anything. So that's what sp2 hybridized carbon atom is. So basically it's got one sp2 electron, sp2 hybrid electron. It's got another sp2 electron, and it's got another sp2 electron. Whereas the fourth orbital it's a p orbital. It's a p orbital that remains unchanged. So that one is unchanged, and that one is involved in pi bonding. So it's involved in pi bonding. So basically what's going on is the carbon initially had 4 electrons, 2s1, 2px1, 2py1, and 2pz1. But 3 of the electrons got pulled in 3 different directions, so their shape changed. So you just gave them different names. You just started calling them sp2 hybrid orbitals because their shape was different. And you gave them the same name because their shapes were identical. So is that clear? sp2 hybridization, is that clear?
Yes, sir.
Yeah.
So what happens when it forms a double bond? There would be 2 atoms that would be sp2 hybridized. They would form a pi bond in the middle. So they're going to form a pi bond in the middle, and so think of 2 carbon atoms. Here's another one. I'm going to rotate it. These 2 are going to connect together. So there's this other one. And just let me rotate the C as well. So 2 carbon atoms, both of them sp2 hybridized. So they're going to form a sigma bond. The electrons would overlap and they would form a sigma bond in the middle. And electron density would overlap. So that's your sigma bond. Who's pulling the hydrogens over here? Let's say there's an H and there's a Cl, right? And who's pulling the electrons? Who's pulling the electrons over here? There's an H and there's a Cl. And the middle part, they would end up forming pi bonds. So there are 2 ways the molecule can bond with its neighboring molecule. So that's one way. Now the other way is that it could bond with another one, but the only difference would be that when the bonding took place, the H and Cl were pointing in some other direction, like the Cl over here. Before the sigma bond was formed, before the pi bond was formed, the Cl was over there and the H was at the bottom. So there are 2 ways where the neighboring carbon, sp2 hybridized neighboring carbon atom could bond. So they could either connect in that way or they can connect in this way. The Cl and H are now pointing in opposite directions. So they're going to come and they're going to bond, and the middle part they would form a sigma bond. And there's going to be overlapping that would happen above and below. That would end up forming pi bonds. The same thing would happen over here as well. Now the point I'm trying to make here is that when this bond was forming, in the first molecule, the 2 hydrogens on the sides, they're pointing in the same direction. They're both pointing upwards. In the second one, the second carbon atom connected in a different orientation, which made the 2 hydrogens point in opposite directions. Is the idea clear?
Yes, sir.
Yes.
So the shape is now different. Although the H is still bonded to the same carbon atom, that H is still bonded to the same carbon atom, and in that H, the H is pointing in the upward direction, and it's in alignment with the neighboring carbon atom's H. But over here, the neighboring carbon atom's H is pointing over here. This H is pointing downwards. So they're basically pointing in the opposite direction. So the orientation or the 3-dimensional shape of the molecule is kind of different. Orientation of the bonds is different because your Cls and your H are pointing in different directions. No matter how you rotate this, it can't appear to, it can never look like the one that's above. And we told you that around the pi bond rotation, independent rotation is restricted. So I can't just twist around this side. Like we did discuss this. So what I can't do is I can't just twist one side. I can't just make this H go upwards and make it look like that. Because if I rotate it, the pi bond has to break. independent rotation of one side is not possible because of the overlapping that's happening, because of the alignment that has taken place over here. If you try to rotate one side, then the double bond would break in the middle. If you try to rotate it anyways, the whole molecule would rotate. This H would go up, but the other H on the other side would then get rotated 180 degrees and it would be pointing downwards. Is that clear?
Yes.
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 So pi bond restricts rotation. So this is one of the key reasons they're going to ask you sometimes. They do ask you why cis and trans molecules are formed. So cis ones are the ones where the H or the same type of groups are pointing in the same direction. So that's your cis. And trans molecules are those where the same type of groups are pointing in. I mean, they're pointing in opposite directions. So one of them is cis and the other one is trans. And we can draw a simplistic diagram with the shape because they're going to ask you to draw the shape. So the shape around the double bond is fan shaped. So fan shaped, like if I don't show the pi bond, it looks, this is fan shaped. The angles are 120 degrees. So in one molecule, the H and Cl are pointing in the same direction. I mean, over here, the Cl is also pointing downwards and the H is pointing upwards. That's your cis version. And that would be known as, I mean, before the name of the molecule, you're just going to write cis. This one is ethene, it's dichloroethene or 1,2-dichloroethene. So you just write cis in front of that, in front of the name. The other molecule would be the same around the double bond. That's the first thing when they ask you to draw the shape of the molecule. That's going to be the first thing that you're going to do. You're going to draw this double bond. And then what you're going to do is, I mean, over here, there's H and you've got a Cl. Over here, the Cl is on top and the H is pointing downwards. So that one is now a trans version. That's trans 1,2-dichloro. Ethene. So two molecules are formed. The connections are the same, but the arrangement kind of looks different. So is that clear? This one.
Sir, the restriction is for trans and cis for both?
Because once the double bond is formed, so I mean, this molecule cannot become this molecule. Do you get the point? Like if
Yes.
I can't turn this molecule, I mean, once the pi bond is formed, right? I mean, before the pi bond had formed, I could have done that because free rotation is possible around the sigma bond. I mean, I can rotate this side and attach it in whatever position I like, right? But once the pi bond is formed, rotation gets restricted. Like I can't twist this H and make it go upwards. I can't just rotate this side because the pi bond in the middle part has locked the other side in with it. Do you get the point?
Yes, sir.
Yeah.
So I can't once the pi bond is formed, this molecule would always look different compared to this molecule. Even though the hydrogens are bonded to the same atoms, over here the hydrogen is still bonded to the same atom, but with there the direction of the bonds is different. Over here the direction of the bonds is also different. Okay, is that clear to everyone? Muneen, Mikal, is this clear?
Yes, sir.
Yes, sir.
Okay, so you've got two types of molecules, and they're going to ask you frequently to draw the shapes of the molecules. So I'm going to do the shape for this one. I mean, you don't have to draw the whole. I mean, they're obviously going to ask you to draw pi bonds, but that's a different story. We're not talking about that. I mean, we did that earlier. That if they ask you to draw the pi bond, what you do, if you see a double bond, just draw this thing. Like make two p orbitals and overlap them above and below. But that's a different story. We're not talking about pi bonds at the moment. They'll ask you to show the cis and trans version of this molecule. So the way you're going to do that is you're going to take this molecule and you're just going to focus on the double bond. That's it. So double bond. Around the double bond, make sure you know what the shape is. It's fan shape. So one bond is going to be over here, 120 degrees. The other bond would be pointing in this direction. Same thing over here, one bond here and one bond pointing over there. And so every time, that's the first thing that you're going to draw. Whenever you're being asked to draw cis and trans. One of them would be your cis version, the other one would be your trans version. So what are the groups that are attached on one carbon atom? That's CH3 and H. So on one side there is CH3, on the other side there is H. What are the groups attached on the other carbon atom in the double bond? That's H and CH3. So which version have I drawn in this case?
Trans.
That one is trans. And the other one, if you want to draw the other one, so that would be the cis. The only thing you have to do is just flip one side. I mean, take the trans and change one of the sides so that the H's are pointing in the same direction, and that's your trans molecule. So you've got a cis version and you've got, sorry, this one is the cis version. So the name of the molecule is, I think it's butene, like this is butene. 1, 2, 3, 4 carbon atoms in a line. So that's but and double bond on the second one. So that's butene. So the name of the molecule is going to be cis-butene. The other one is going to be your trans-butene. So you've got a cis-butene and you've got a trans-butene. So we're going to try and do questions as well. I'm going to try and do some questions first. And then we're going to talk a bit more about this thing, about cis and trans. Just a second. Where are the questions? So there's some questions here, isomers. So there's only one left, which is optical isomers, but there's some details left about cis and trans. But after doing these questions, so here, for example, there's a molecule. Can you spot, will this form cis and trans or not? This molecule over here?
No, it won't.
No, sir.
It won't because it's got the same type of groups. I mean, you need a double bond, but each carbon atom must have different groups, which in this case, they don't have different groups. They actually have the same group. Like if you just rotate one side, it would still be the same thing. As anyways, name the stereoisomer shown by, so they're saying, this one is more about optical. So let's ignore that. And the same over here, this one is not going to form cis and trans, right? Double bond, but both groups are exactly the same. And remember, all 4 groups can be different as well. I mean, the minimum condition is that each carbon atom must be bonded to 2 different groups, and this carbon atom must be bonded to 2 different groups. But there's a possibility that all 4 groups are different. They would still form geometric isomers. So anyways, let's say is there, that's chiral. Just a second. Let me open another worksheet. Just there's a pair of stereoisomers. 1 second. So which one? So you're saying what type of stereoisomers is this? Type of stereoisomerism in R?
Geometric.
Geometric cis trans, basically. So remember this one. This one will form geometric isomers. Like it's got double bonds, and both sides are different. What version is that? The one that's drawn over here.
Trans.
Okay, that's your trans version, and they're asking you to draw the structure of the other stereoisomer.
Sir, but how is it?
How is it?
Oh, never mind. Never mind.
So they're asking you to draw the other version. So what you can do is you can keep one side the same, just flip the other side. So the other molecule is going to have keep one side the same, flip the other side. So this other molecule will have the H's pointing in the same direction. That's your. So I've just flipped one side. I mean, the other molecule is going to have the other side arrangement would be the opposite, and that's your cis version. Displayed optical. That's too many questions on optical. Just a second. So let me open the. So let's try and do this one. Now this one has this one is about cis and trans. This question is kind of difficult. It says how many structural and cis trans isomers are there for dichloropropene. Now we're going to talk about cis and trans later. We're just going to focus on structural isomers first. We're going to draw structural isomers. So C3H4Cl2, right? So C3 would be 3 carbon atoms, H4 and Cl2, right? So Cl2, 4 hydrogens. So that's it. C3, 4 H's and 2 Cls. Should there be a double bond in this molecule?
Yeah, it's propane.
Yes.
Okay, why? Because it's I mean the bonds are not getting completed. I added 4 hydrogens, I added 2 Cls, but I was missing atoms. So there must be a double bond, right? So that's one structural isomer. What else can I do? I'm going to try and draw all of them. What else can I do? I can keep changing the position. I can't have a chain isomer with 3 carbon atoms. That's kind of impossible because I mean you can't alter. I mean you need at least 4 carbon atoms to alter the chain. You can't do that with C. So what I can do is I can have positional isomers. I can keep changing the position of the Cl. So that's one. These are all my H atoms. The other one would be that I can have the Cl on opposite ends, like keep this one over here and put the other Cl on the extreme left. And the rest are all hydrogens. Is that clear so far?
Yes, sir.
Yes.
Yes.
So what else I can do? I can have I can remove the Cl from one end and put them over here on the first 2 carbon atoms. So this one will have. The last thing I can do is I can put both Cls on the extreme.
So can you not change the place of the double bond?
I can do that as well. Now, but the thing would be, I mean, first let's focus on the Cls. Is that all? Can I do any other combination of Cl? Like 2 Cls over here on the right side on the double bonded carbon atom, 2 Cls around the double bond, 2 Cls, one on the extreme right, one on the extreme left, 2 Cls on the left one carbon atoms that are not making double bonds. And then I've got 2 Cls on the extreme left. I mean, this one is different from this one because these are not bonded to double bond. These ones are bonded to a double bonded carbon atom. So these two are different. So is there any other possibility for Cl being any other place?
No.
Okay,
No.
that's probably not. Now the thing is that if I flip it, if I change the position of the double bond, it's basically going to be the same molecules just flipped around. Like let's do this one. Like if I change the position of double bond, like I could have changed the position of the double bond earlier, but once I've rotated the Cl everywhere. If I change, I mean you can try this. If you try and change the position of the double bond and keep everything else the same, kind of the same, like the Cls over here. Now what will happen is this particular molecule looks exactly like, which one does it look like? It looks like this one.
Yeah, the second last one. Yeah.
See, it's this one looks exactly like this. Like it's got a Cl on the carbon. It's just a flipped around version of that. So the point is in this case, no matter what you do to the double bond, it always looks like a flipped around version of a previous molecule that you have drawn. Is that clear?
Yes.
Yes. Yes.
So this one is not. I mean, these two are exactly the same. Anyways, so I've made my structural isomers, right? But he said,
Sir, do we have to try? We can try also this cyclic one for the structure.
just one. How many structural isomers and cis trans isomers are there for dichloropropene? Can you make a cyclic? I mean, you should be able to make a cyclic. Actually, there's this issue with this question, I think. Just a second. 3 carbon atoms in a row. So 4 H's and 2 Cl's, right? So let's say 4 H's and 2 Cl's, right? So you can, I mean, you can make that. But I think, I mean, the question was basically, I mean, there's one subtle, I mean, they should have been more clear about this, but the question kind of states, or what it implies is that everything should be a dichloropropene. Like every molecule that you draw must be a dichloropropene. So they're basically focusing on the fact that you should just change the Cl positions, like the propene is there. So that is kind of implied in this, but they should have been more clear about that. Is that clear?
Yeah. Okay. Got it.
So the question was vaguely hinting that it wasn't clear about that, but they're basically looking for that every molecule that you draw is a dichloropropene. This is the propene dichloro, only the position is different. So anyways, we've drawn the structural isomers. Now the next thing is we need to figure out which ones are forming cis trans, because the ones that are, they would be existing in 2 forms. So which one do you think is forming cis trans? The first one, is it cis trans?
No.
What about the second one? Is this cis trans?
Yeah, maybe.
Yes.
Because it's got a double bond, and each carbon atom is bonded to 2 different groups, right? So this molecule would be counted twice, because there's a cis version of this molecule and there's a trans version of this molecule. What about this one? Is this cis trans?
Yes.
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 See, so that's also cis trans, 2 different groups on the double bond, 2 different groups on the double bond. So this one would be counted twice. There's going to be a cis molecule of this, and there's going to be a trans. This one.
But sir, that means so many. It's 1 to 5.
Huh?
There,
Also, this,
Yeah, I didn't get you.
There-
It
there's
makes
like
9
nine.
isomers.
Yeah, we'll discuss that. This one is not going to form cis trans, right? 2 H's, right? This one is also not going to form cis trans, right? So how many total isomers do you have now? So that's 1, 2, 3, 4, 5, 6, 7. Is that clear?
Okay. Yeah, got it.
I mean, I think you're counting this thrice. It's not counted thrice. It's, I mean, this molecule, this molecule will have a cis version and it's going to have a trans version. There's just going to be 2 versions of this molecule. Right? So,
Got it.
and this one would also have just 2 versions. One of them would be cis, the other one would be trans. So that's 1, 2, 3, 4, 5, and 6, 7. So the answer would be D. So, so is this clear to everyone, this one?
yes, sir. It's clear now.
Yes, sir.
So then we can have a lot of questions about chirality. Chirality, just a second. So this one, let's do this one. C2H2Cl2, right? I mean, that's probably an easy one. C2H2Cl2, seeing including cis trans, like you have to include all of them, not just structural. So C2H2, C2, I mean, it's probably a double bond because there's just two H's and two Cls. So how many versions for this molecule?
2.
So there's a cis version and there's a, so basically this is two molecules, right? What other arrangement can I have? I can have two Cls on one side and two H's on the other side. So that's not cis trans, right? So basically,
Yes.
and is there any other arrangement apart from these two, like structurally?
No.
No.
No, so that's one, and this would be two. There's going to be a cis version, there's going to be a trans version. So the answer would be
3.
3. The answer would be 3. So let's continue tomorrow. We'll probably do optical isomers, be done with that, and we'll practice more questions. There's just one thing left in cis trans, which is if a molecule has multiple cis trans. So we'll do that in the next class.
Okay, sir.
Okay, sir.
Okay.
Allah Hafiz.
Allah Hafiz.
Okay, take care.
Thank
Allah Hafiz.